Good afternoon. My name is Longa. I came from Jagiellonian University in Poland, Krakow. I would like to thank the organizers for allowing me to have this talk. And, you know, the issue of spontaneous carrier symmetry breaking is a very hot subject nowadays. So I would like to show you the answer from the Landau-de Gennes theory on that question. How can we break carrier symmetry within Landau-de Gennes sort of approach? Okay. So outline of my talk is as follows. First, I will recall what Landau theory is, and then I will argue that in order to get carrier symmetry breaking, the lowest order approach would require secondary order parameters, and that could be either octupolar field or vector field. Of course, there are plenty of possibilities, but so to speak, the lowest order choice is among these two. And then I will show you some predictions of this theory. Actually, we started this problem as early as in 1990 with Rainer Trebin, and part of these results are actually being discovered nowadays. So let me show you what we have done and what we will be doing in the future, I hope. So in Landau-de Gennes theory, a fundamental assumption is that your liquid crystalline medium is locally described in terms of alignment tensor. It's a traceless and symmetric field. It's a 3 by 3. It's a matrix. Trace Q equals 0 means that in the isotropic background phase, eigenvalues of the tensor are disappearing. That means the reference isotropic state is just described by Q equals 0. As you know from the basic algebra, if we have a Q alpha beta tensor, symmetric and traceless, it's characterized by 3 real eigenvalues and, of course, the corresponding eigenvectors. When eigenvalues are all equal 0 because of this condition, because of traceless condition, then we have, as I said, isotropic phase. When we have 2 eigenvalues degenerate and 1 non-degenerate, we have a uniaxial medium. The eigenvalue, which is non-degenerate, corresponds to eigenvector, which is known as the director. And finally, we have the third situation where 3 eigenvalues are different, and that situation describes a local medium which is biaxial. As early as in the 70s, de Gennes just formulated a very simple expansion based on this idea that allows us to explain basic properties not only of nematics, but also of holesterics. And this theory comprises actually 3 different sort of terms. Well, the first row here, up here, is the so-called bulk free energy. It is composed, well, I should mention that this expansion is constructed with respect to the background isotropic phase. So the first line is the bulk free energy. It's composed of all SO3 independent invariants. So we have trace Q square, which is weighted by the temperature, as usual in Landau theory. Then we have trace Q cube. This term makes nematic isotropic phase transition first order. And then we have trace Q square squared, which is stabilizing term. Without that, this theory wouldn't be stable. That means isotropic phase wouldn't be stable with respect to large fluctuations. So that's the first line. The second line describes elastic sort of behavior. So actually, it weights fluctuations in this theory. And at the level of the lowest order expansion, we have 2 elastic constants. One of these could be Z1, just by rescaling Q and the free energy, and also by rescaling the distance. So it's a gradient of q squared, divergence of q squared, and the third term, which is rotation of q dot q, is only present for carial materials. In the non-carial material, kappa is 0. So actually, kappa measures, so to speak, on the average, the misalignment of two molecules that have somewhere here carial centers. So that's the theory. If you make a special case, namely if we take Q to be uniaxial, so we have a director, cross director, minus 1/3 a unit tensor, just to have trace equals 0, then if we substitute this sort of approximation to this expansion, then we recover a theory which is known as Osenzocher-Frank. But there will be some degeneracy. Namely, gradient of Q gives us splay and twist and bend weighted with the same elastic constant. They are 3 equal. Divergence of Q would produce only splay and bend. And that, of course, will matter a little bit in our discussion. Now, there is one more characteristic I would like to emphasize. If we have a tensor field, it cannot, of that sort, it cannot vary just arbitrarily. Simply, the whole variation, local variation of that field, is limited by this simple mathematical inequality. Namely, 6 trace q cubed squared is always less than or equal trace q squared cubed. Apparently, the whole uniaxial structures, that means where the tensor is degenerated, are located at the border of this area. On the other hand, all biaxial structures are here in the middle. And you have a beautiful oblate-prolate symmetry in this scheme. So, if I divided square root of 6 trace q cubed by trace q squared to 3rd half, then this sort of parameter will locally be always less than or equal 1 and greater than or equal minus 1. It approaches these limits for uniaxial states. So you see immediately that the state of maximal biaxiality is just trace q cubed equals 0. And that's the situation where oblate and prolate symmetry is being changed. This sort of this sort of description of nematics and holesterics is extremely fruitful because the quadratic part of this free energy can be diagonalized. That means you can make a Gaussian theory of decoupled modes out of that. So if you take trace q squared and the whole elasticity which is in here, it appears that eigenstates of that Hamiltonian are the eigenstate of the so-called helicity mode expansion of spin L equal 2 states. So I will show you this later, but let me show you those eigenmodes, because they are very closely related to cariality. So you make just Fourier expansion, and the coefficients of the expansion that diagonalize the Hamiltonian or the free energy, the Gaussian part of the free energy, are spin L equal 2 matrices. So they transform like spherical harmonics of L equal 2. You see, if you do this expansion, then because they correspond to spherical harmonics of L equal 2, they are so to speak, parameterized by azimuthal numbers, and there are 5 such numbers: m equal plus minus 2, m equal plus minus 1, and m equal 0. These modes are carial. So if you like to describe cariality, it is sufficient that the expansion coefficients are having different weights for m equal, say, plus 2 and m equal minus 2. And that would be a sign that our system breaks the cariality. So for carial states, these amplitudes simply for opposite m's are different. I showed you the illustration here. What those bricks mean? You just take the helicity modes, multiply by exponent I car r, then you diagonalize it, and you make a brick of arms which are moduli of eigenvalues. If you do this trick, then you get these pictures that I showed here. So you see that for the mode m equal 2, it's a cariality mode where the main director is always perpendicular to the k vector. For the cariality mode m equal 1, the eigenvector, eigenstates are under 45 degrees with respect to the k vector. And m equals 0 is, of course, non-carial mode. So that's the basis. I will show you how holosterics look like in this description. For the holosteric phase, you simply have a combination of the uniaxial brick, a uniaxial mode, which is this one, and m equal 2. And you can show that for intrinsic, the mode that is responsible for intrinsic cariality is m equal 2 or m equal minus 2, depending upon the sign of k. And indeed, the holosteric phase is a biaxial phase. You see, here is this parameter w. 1 minus w should be 0 for uniaxial states. So, so close to the transition, depending upon the value of kappa, we have more or less biaxial structure. So these biaxial modes should be seen, for instance, in light scattering experiments. And they do. Now, suppose that our medium is described by such a field. Now the question is, what should we do in order to get carial symmetry breaking? For carial symmetry breaking, which is a new sort of stuff, we need an extra field. Now, it seems that many of us believe that the carial symmetry breaking is correlated with excluded volume effects. So if we simply take 2 bananas and calculate the excluded volume, we will find out that to the lowest order, I should emphasize that there are many avenues that one can follow. But one of these, the lowest order, tells us that for 2 steric bananas, there's nothing else but steric spherocylinders, for instance, connected at certain apex angle. If you do that, and if you calculate the excluded volume, you will find out immediately that there are 2 tensors that could play some sort of role in carial symmetry breaking. And that would be a polar field due to steric polarity of the molecule, or that could be octupolar field. Let me start with the octupolar field. I will not going to talk much about octupolar, but it kind of shows how this business works. So I have my tensor, I add octupolar tensor, and how could I make these 2 things combine together biaxial? That's very easy to see. You simply take the octupole, put a biaxial brick inside, and try to mirror project this object. If you do mirror projection, then you cannot, by proper rotation, bring this guy into that one. And that is the, so to speak, that shows that indeed that sort of combination brings us cariality. How could we quantify this? Well, the simplest way is to calculate pseudoscalars. Because if I have basic fields of this sort, and if they're supposed to produce something which is carial, I should be able to produce pseudoscalars. The simplest pseudoscalar is, of course, tensor proportional to Levitch-Vita symbol. And with Q square and T, I indeed can produce such a thing. And therefore, I can produce, but there is a requirement. It cannot be arbitrary. If you do this contraction, By the way, the square brackets means anti-symmetrization with respect to alpha, beta, gamma. For other indices, I assumed simply Einstein summation convention. With this in mind, you find out that indeed this sort of tensor will exist given that Q is non-zero, T is non-zero, and Q is biaxial. It's square root of 1 minus W. So when W, this parameter between -1 and 1, is exactly 1, this sort of pseudo-tensors cannot be constructed using these two things. And actually, that was already discussed long ago by Lubensky and Radzichowski. Okay, so that's this field. How about polar field? With polar field, we have the same actual story. If I take a polar vector, then I first take a, so this polarization gives me one direction in space. Let's say, let's assume that it has a red color. Then, multiplying Q with P gives me the second vector, which would be different than the first one. It would be simply, say, green. And square of Q times P gives me the third vector, which would be completely different than the other two. So I get three vectors of different colors, and of course they define causality. And again, if you do calculus, you will find out that you cannot induce causality if these objects, if Q is not biaxial. So biaxiality is extremely important. But also, the polar vector cannot be an eigenvector of the tensor Q. And also, it cannot lay in plane of two directors. Okay, so that's the limitation. So with this information, we started our studies. We expanded the Landau-Desgen's theory using a polar field. Then you get the characteristic temperature Tp connected with the polar field. You get gradient of P squared and divergence of P squared. You also can get P squared squared. That's the lowest order, purely polar part that should be added to the free energy of Landau-Desgen. Then we have flexo-polarization-like term, P divergence of Q, and the bulk term PQP, which is also non-zero. So the lowest order theory should actually have all of them. We have studied that theory long ago, and we reconsidered the model again after Dave and Jonathan paper last year, where they showed that this sort of theory can also bring a blue phase sort of stuff. So then we started to study in more detail one-dimensional periodic structures. And let me show you some results. So first, assume that there is no higher order terms, that there are only quadratic terms. Then when P appears quadratically in the Hamiltonian, I can simply take it off, take it away. I can minimize the free energy with respect to P for given fixed Q. And if I do that, I just simply modify the quadratic part of the free energy. Well, let me not go deeply to details, but I will show you what follows from that minimization. And namely, you get the free energy, which is totally expressed in terms of amplitudes Qm, which were on one of the first transparencies. And because we eliminated P, the price we pay is that our elastic free energy gets infinite number of terms. The lowest order term, which can be recovered from that expansion, is simply renormalization of the divergence of Q. It does not affect the first one. It means that with the non-zero P vector, we can only generate splay band sort of one-dimensional structures. You cannot generate twist with this sort of coupling. So at this level, twist does not exist, but only splay and band structure. And maybe you may ask, what happens when I take octupolar tensor? OK, I will show you just result without going into details. If you take octupolar tensor instead of P, then you have octupolar sort of flexo coupling, and you have the corresponding temperature that weights the quadratic part. Doing the same tricks as I showed, elimination as I showed you, you renormalize the gradient of Q. You also renormalize, of course, divergence of Q, but it's important that you renormalize the gradient of Q. So for certain value of this coupling, you can destabilize gradient of Q, which means that you can get cariality without going further with the expansion. So in this sense, the T tensor is much powerful because it can generate cariality even at the quadratic level of Landau-Desgen's sort of expansion. But what about 1 minute, right? What about OK, I will show you, because my time is nearly over, I will show you some figures as concerning splay band instabilities that follow from the model. So for certain values of parameters, you can get a bunch of new structures. One of them would be nematic transverse periodic. All situation takes place in plane. Arrows show the change of polarization while the polar field, while bricks are, as previously, eigenvalue of the Q tensor moduli of them. So you see, you have a planar splay band-like structure. You have new one, which is nematic transverse periodic. Then you may ask what happens with those structures when the intrinsic molecular cariality takes into play. Then, if you switch on intrinsic molecular cariality, you get twist band phase, and you get new carial splay twist and band phase as well, in addition to standard holesteric. Now, non-zero lambda introduces new thing into the problem, namely, for non-zero lambda, you can actually force the splay band structure to go off-plane with the main director. And therefore, you can generate splay band and twist band structures via bang. No, it does not like. OK, so with this sort of scheme, using bulk terms, you can generate cariality as well. But for that, you need higher order terms. So you need a coupling which is dielectric-like, OK? PQP. But there is also one, I think, in my opinion, interesting solution that follows from this theory. Namely, even for carial systems, you can get non-carial structures. So you can expel cariality. And that's when the mode m equals 0 gets into competition with m equal 1 mode. So that's you can get longitudinal periodic wave, which competes with splay band. But when you add cariality, longitudinal periodic wave will stay still stable, while you get carial splay band twist structure instead of splay band. OK, so I think my time is over, really over. So thanks a lot for your attention.
There's a question. OK, Sergey.
Can you explain, if you don't have difference between spray and band constant, how you can distinguish between spray band and twist band? So spray deformation and bend deformation.
Actually, you can't. Because they are equally weighted. You can't. That's, you know, you have to go to higher orders with the expansion in order to distinguish between them. At this level, that's the price you pay. You have a nice helicity mode expansion formalism, but you have degeneracy of elasticity. So,
yeah, but you took a lot of high order terms.
No, on the contrary.
You have Q terms in Q at some moment.
Because we want to have pneumatic state described somehow. You cannot, it's unavoidable.
I'm not talking about main terms. I'm talking about terms associated with forward.
With the secondary order parameter. Okay.
Yes.
So if you stick only to quadratic part, the model is exactly solvable, as I showed. But then you get only splay bend sort of structures. You don't get cariality. And that's exact. It's no approximation, except for the helicity mode expansion and except for assumption that you end up with elasticity at quadratic order in the order parameters. Okay? But you still can get cariality given that you include higher order terms like P alpha, Q alpha beta, P beta. That's unique. This is like dielectric-like sort of coupling, right?
No, I agree.
Yeah.
Okay. So maybe we need to like keep the schedule a little bit behind. Okay. You know, I'm sure a lot of people also have more interesting. Then after, you know, maybe the break times, the talk Professor Longa again. Thanks very much.